as this is the continuation of 9.2. Let's see where we were. All right, so let's look at this series. 2 over 1 plus 2 over 5 plus 2 over 25 plus 2 over 125 plus 2 over 625 plus dot, dot, dot. See if you can write the sigma notation expression for this series. So in order to do that, what we want to do is come up with an nth term for this. So if this is the first and second and third and fourth terms and fifth, what were we going to do to n to get that answer each time? So you'll notice that the numerator is not changing. It's a constant, so it will be 2. And I see that this could be seen as powers of 5, except for that first one. It kind of bothers me. Well, I'm going to write powers of 5, and then I can adjust it in a second if I need to. So that's the nth term, I think. Except for, no, that doesn't start right. Because if n is 1, that gives me 2/5. And that's the second one, not the first one. Well, there are 2 fixes for this. I want to talk about both of them. One is if you're just bound and determined to use n starting with 1. And that's not a bad thing to do that, because that's going to be what we do most of the time anyway. Then that's not the right expression. Down here I'm going to write the correct expression. I need to start with 5 to the 0. So what would I need to do to n, like 3, to turn it into 5 squared? What would I do to 3 to make it 2? Well, I'd have to subtract 1 from that exponent. And so that's one way to deal with this. So the first number you put in 1, 1 minus 1 is 0, 5 to the 0 is 1, and there's your first term. That's if you're going to start with n equals 1. However, if you want to stick with this simpler expression, 2 over 5 to the n, to get this one, this is where we might want to start, not counting with 1, but with 0. And this is one of those instances where the change of that lower bound might feel like it's easier than changing the formula. In essence, it doesn't really matter which one of these you do. So they're both correct. They're just 2 different expressions for it. And in fact, they're actually more than that. We could have n minus 4 and start with the correct n so that we got 5 to the 0 eventually. Or whatever we wanted that exponent to be, n plus 6. Then we could start n at a certain place, so the very first one would be come 5 to the 0. So at any rate, those are not as common as the 2 that I have here. These are the most common of the 2 possibilities. Now, what I want to focus on now on this problem is a recursion thing. Recursively speaking, what are you doing to each term that provides the next term? So in other words, I'm not looking for this explicit formula out here. This is not what I'm interested in, because that's the explicit thinking answer. But what are we doing to each term to get the next one? Well, hopefully you're seeing that we're multiplying by 1/5. If we multiply by 1/5, which is the same thing as divide by 5, by the way, if you multiply by 1/5 every time, that produces the next term. Okay, so let me write that down. Recursively speaking, so recursively, we obtain, in this particular example only, we obtain the next term by multiplying the last term known, the last term we have, all those are synonymous. You multiply this last answer, the last term, by 1/5. And anytime your pattern is that particular pattern, but perhaps it doesn't have to be 1/5, by some constant. And so generically that we're going to call that constant R. R is the common ratio. That's why it's R. It's the common ratio. Let me explain where that term came from quickly. If I were to take any term I want except for the first one and divide it by the one right before it, man, I said one thing and did a totally different thing. Take the any term you want and divide it by the one right before it, you'll get that common ratio. So like if I divided 2 over 125 by the one right before it, 2 over 25, the answer I get is 1/5. So that's what every pair of terms in this series do, is that the ratio of those, later one divided by the early one, is always the same number. It's a constant. And we're calling that constant R. And when there is this pattern, every time you see this pattern, that you're obtaining the next term by multiplying by a constant, which we're going to call R, this is what we call a geometric series. That's the type of series this one is. And did you hear me say earlier, if I name a type of series for you, your ears should probably perk up and you should probably be thinking, that's something I got to know. And yes, this is one of those that you definitely need to know. So let's build a generic geometric series, if you would, with me. So we're going to do the nth partial sum of that series. So if the first term is a letter like A, just some constant, then we're going to multiply that by R to get the next term, so AR, and then multiply that answer by R to get the next term. AR times R is AR squared. Multiply by R, AR cubed, etc. And that ends up being the last, when we do the nth one, we need to think about this. This is going to be A times R to some power. It's that unknown power that I want to think about here for a second. So this is the first term, and the second, and the third, and the fourth terms. So when I get to the nth term, if I want to put an n up here, how is that number in green above related to the power of R? Hopefully you're seeing that the exponent is always that number in green minus 1. That's what that should be. Okay. Now, since that's an equation, and we're going to assume that it's a true equation because we built this correctly for a geometric series partial sum. Since it's an equation, we learned in algebra that we can do whatever we want to both sides, well, within reason, as long as we do the same thing to both sides. So what I would like to do is multiply both sides of this equation by R. Oops, didn't mean to write that last thing. Okay, we're multiplying the right side by R. And that multiplication by R is going to be distributed to every single one of those. So A times R will be AR. Notice that that answer slid to the right. And then the second term, AR times R, is AR squared. Slid 1 to the right. AR squared times R is AR cubed. AR cubed times R is AR to the fourth. And then we'll keep doing that. And if these are sliding over, oops, I didn't leave myself enough room. These things aren't going to line up nicely, but I'll try to make it work. Isn't the penultimate one above, the second to last one above, when multiplied by r, going to give us the same as the last term above? Because they're sliding over one. And then the last term times r is going to be a times r to the nth. Because you multiply powers with the same base, r to the n minus 1 times r. You add the exponents, n minus 1 plus 1 is n. Okay, then another thing we know we can do is we can subtract the same thing from both sides of an equation. So since those are equal, that second line is the left side equals the right side. Since they're equal, I can subtract the left side from the left side and the right side from the right side. So that will give me S sub n minus rs sub n on the left side. A minus a 0 below it is a. AR minus AR is 0. This sounds like a telescoping thing, doesn't it? AR squared minus AR squared is 0. AR cubed minus AR cubed is 0. And we'll continue getting a bunch of zeros until AR to the n minus 1 minus itself is 0. And then finally, we'll need to think of an understood 0 up here. 0 minus AR to the nth is, hold on, I made a mistake. It's not a plus because we're subtracting, so 0 minus AR to the nth ends up being minus AR to the nth. Okay, now on the left side, I'm trying to solve for S sub n and get that nth partial sum formula. On the left side, it is a common factor, so I'm going to factor that out, leaving 1 minus r. The right side collapses to become a minus ar to the nth. And since we factored on the left side, that sounds like a great idea. Let's just go ahead and factor on the right side as well. That common factor a can come out, leaving 1 minus r to the nth. Notice where that exponent is. It's on r. It's not on the binomial. This is not 1 minus r close parenthesis to the nth. Be very, very careful here. Then, to solve for S sub n, I just need to divide both sides by 1 minus r. Now, notice here, since we're dividing, we always have to be careful about division by 0. Can't let that happen. So we can't use r equals 1. That's just not going to be a happy camper. That's not how we would do that because we can't divide by 0. Okay. So I want to know if the geometric series will converge. So I'm going to take the limit as n approaches infinity of my S sub n formula. Now keep in mind, this generic problem, a is just some unknown first term, just a constant, and r is the common ratio, also just a constant. So the only thing changing here is r to the nth. And we have two cases that we want to deal with. Two cases. One, what if the absolute value of r is less than 1? Well, in that case, the part of this that is the only part that's changing, and I'll come back to the original problem in a minute, is the r to the nth. If you have, say, like 2/3, and you're multiplying it over and over and over, 2/3 to the huge number. If you do that on your calculator, like 2/3 to the 20th, and then 2/3 to the 100th, and then 2/3 to the 1000th, you'll probably notice that when you multiply that kind of number by itself over and over again, it's headed towards 0. Absolute value of r, so that's a way of saying, by the way, that's the same thing as saying -1 is less than r is less than 1. As it turns out, if r is a negative number between 0 and -1, the limit of that would also be 0. So this is a true statement for what we have. Now the other case, the next one's actually kind of 2 and 1, but I'm going to combine them into one idea. What if the absolute value of r is greater than 1? Well, think about it. If r were, say, 2, and you multiply 2 times 2 times 2 times 2 infinitely many times, what's going to happen to the limit of r to the nth as n approaches infinity? Well, that's going to be infinite, which means that the limit of the sequence of partial sums diverges. So the sequence of partial sums diverges in that case. And that means that the series, the geometric series that we're talking about, diverges. So if the absolute value of r is greater than 1, you know that the geometric series will diverge. And that's good news, because you won't have to go through that whole argument we just went through. All you have to do is test, well, what's the value of r? Or actually, what's the absolute value of r? If you can find an answer that's greater than 1, like -6, the absolute value of -6 is 6, which is bigger than 1, then it will diverge, for sure. Excuse me. Actually, I guess I probably should have made this 3 cases. In hindsight, I'm now thinking maybe that would have been smarter. So let me go back up here and change this into 3 instead of 2. You'll see why I was thinking 2 in just a second. I'm not trying to befuddle you at all. I'm just trying to make this concise, and kind of messed up because there are really 3 cases. So if the absolute value of r isn't less than 1 or isn't greater than 1, what else is left? Well, the absolute value of r could be equal to 1. It's a concept of trichotomy. When you compare numbers, there can be a less than relationship, a greater than relationship, or an equal relationship. And that's the only 3 possible ways to compare 2 numbers. So that's it. That's everything that can happen. Well, if that's the case, it's really not a geometric series. It's not a geometric series, really. So that would be, because if you just multiply by 1, that means that whatever your first term is, times 1 is it. And times 1 is it again. So this would be that first term times 1 is plus that term again, plus that again. So this is not acting like a geometric series. And because if you continually add something to itself, it's just going to grow towards positive infinity, or if a is negative, go unbounded towards negative infinity. And so in this case, this series would diverge. Series diverges. Okay. So what I was intending on saying, the conclusion is, if the absolute value of r is greater than or equal to 1, the series diverges. So the first thing you're going to do is identify it as geometric. and tell me what R is, and then make a claim about what the absolute value of R is compared to 1, and then if it's greater than or equal to 1, then you'll say therefore it diverges. If it converges, if absolute value of R is less than 1, that's actually going to be convergent. So let's go back up to that that limit that we were working on of the sequence of partial sums. If we have the limit, or first of all, only if we have absolute value of R less than 1, this is the only time this does this. So that's a necessary condition to do what I'm about to write. Then the limit of the constant A will be A. The limit of the constant 1 will be 1. We've already established that the limit of R to the nth will be 0 over 1 minus R. And that simplifies to be A over 1 minus R. A over 1 minus R. And since that's what it converges to, that's the sum of the convergent geometric series. And that's a really important formula for you to realize. If you have a geometric series, and if the absolute value of R is less than 1, then the geometric series will converge to the first term A divided by 1 minus the common ratio R. We've now proven that. Okay, in the beginning of the other video over this section, we were looking at a couple of series, and I said we'd come back to them, and I don't want to make a liar out of myself. So the first one, I believe, was 1/3 plus 1/9 plus 1/27 plus ... And if you look at this carefully, this appears to always be found, the next term is always found by multiplying by a constant. It's always times 1/3 to get the next term. And so because of that, we'll then say, when we look at this series, I need for you to tell me that you recognize that it's geometric, because that then puts us into the geometric series test. So that's something you want to make sure you do, is when you recognize the type of series, tell me what type it is, and that means you're about to enter the geometric series test. And for the geometric series test, I will require that you tell me what R is, and what is the common ratio, the common number that we're multiplying by to get the next term each time. It's 1/3. Then I want you to say something like, since or because the absolute value of R, notice I'm not writing absolute value of 1/3, but generically for this problem, we're saying that the generic absolute value of R is less than 1. That's a test statistic for this test of geometric series. I want you to tell me that in terms of R, which one of those you got, absolute value of R less than 1 or absolute value of R. The other possibility is this one right here, which will take us to that conclusion, but that's not the case here. Since the absolute value of R is less than 1, the sigma, I believe this was n equals 1 to infinity of 1 over 3 to the nth. I believe that was the name of that series. Converges. And it converges to S, which, if we look at the formula up above, it's A. Oh, the other thing we should identify here, by the way, is what's the value of A? What's the first term of this series? It's 1/3. So S is A, 1/3, over 1 minus R, 1/3. So 1/3 divided by 2/3 is 1/2. And so if you have a geometric series, it's very possible that coming up with that S sub n formula, which I kind of fumbled my way into, where that numerator was half of the denominator minus a half, if you'll recall that one, kind of an odd one. This is way simpler than going through all that process. So if I'd identified it at that point as geometric to begin with, we could have done this, and this is a complete test. So the next one, I believe, was the denominator was powers of 2. Trying to remember, I think that's right. And of course, I think we can safely say that we think this one is geometric as well. And what is R? What are you multiplying 1/2 by to get 1/4? What are you multiplying 1/4 by to get 1/8? The answer is 1/2. And this time I'm going to remember and locate or define for me what your first term is. So, since we have one of two possible statements, we're either writing the absolute value of R is greater than or equal to 1, if that's true, or the absolute value of R is less than 1, if that's true. The absolute value of 1/2, this R in particular, is less than 1. So that means that the series n equals 1 to infinity of 1 over 2 to the first, to the nth, excuse me, converges. And it converges to the sum S, which is the first term 1/2, divided by 1 minus R, where R is 1/2. So that's 1/2 divided by 1/2, which is 1. And that's the same answer we got before. So in both cases, this procedure is way faster. So when it's a geometric series, this is the way you want to do it. That's 2 complete tests for the convergence of a series. And we actually also found the sums. And whenever you can find the sum, you are required to do so. As it turns out, there are lots and lots of different tests for the convergence of series that we're going to encounter. Very few of them are ones whose sum we can find. And in fact, I think we just about done them all. If you can find a formula for S sub n, like we did with a few examples already in the first video, if you can find a formula for S sub n and take the limit as n approaches infinity of that S sub n, which is the sequence of partial sums general term, if you can do that and get a real number, not infinity, not negative infinity, but an S sub n that leads us toward a constant S, then we could say that it converges to that number. Most of them we won't be able to do that for. So the geometric series, we can find S. We already talked about the telescoping series and how we could find S. And only if you could find a formula for S sub n, which is very doubtful. Most of us won't be able to find those very often. So for most of the rest of them, you will not be asked to find the sum because there's no way to find it. You can approximate it, but you can't find it most of the time. We're just kind of lucky that we can in this case. Okay, so let's go to example A. By the way, a lot of times we're going to start geometric series with 0. That's so that our exponent can be simple instead of complicated. Remember up above, at some point I told you we could have started at 1 or 0. Let's see if I can find that really fast. Oops, not too far. Yeah, that top one, we could have started at 0 or 1. Notice that when you start at n equals 0, it's 5 to the n versus 5 to the n minus 1 if we start with 1. So most of the time we are going to start n with 0 It makes life simpler. Just trust me. I promise it's way better. And in fact, the way that geometric series are defined in that Theorem 9.6 has it starting at 0. Again, that's for algebraic ease. That doesn't mean all of them will look like this, per se, but they're all equatable to this. And so if you put in 0, r to the 0 is 1, a times 1 is a, and you get that first term, right? Et cetera, et cetera. Okay. At any rate, this one, it's not quite written in that form. What we want to see is a constant, which we're going to call a, times some common ratio to the nth. This first time, I'm going to do it by thinking of it numerically. So 2 to the 0 is 1. So 3 over 1 is 3. 3 over 2 to the first is 3 halves. 3 over 2 squared is 3 fourths, etc. Now that you have those numbers to look at, you might notice that the common ratio is 1/2. And the first term is 3. And it's geometric, which I kind of implied when I said r equals 1/2, but I do want you to state it. So since the absolute value of r in this problem is less than 1, the series that we were given converges, and what it converges to is called the sum of the series S, which for geometric series that converge is a, which is 3, divided by 1 minus r, 1 minus 1/2, which is 6. So the sum of this series is 6. What I started to say and backed off for a second is that's just expand the series a little bit so that when you look at the numbers you go, oh, obviously geometric. I can identify a, I can identify r, and I can test r and see if its absolute value is less than 1, which means it'll converge, and I can find what it converges to using the formula S equals a over 1 minus r, or because the absolute value of r is greater than or equal to 1, it diverges. So that's one way to do this. Another thing I want to point out is that instead of doing the numerical process that we just went through, you can do this a little bit more algebraically. It's kind of a little bit of a trickery thing. So that original sigma can be rewritten as 3 times 1 over 2 to the nth and since 1 to the nth is always 1, I can think of that as 3 times 1 to the nth over 2 to the nth. And because of the property of powers on ratios, or on quotients, on division problems, in reverse, I can think of that as 1/2, the fraction 1/2, raised to the nth. And that's now in the form where I can say, oh, there's a, there's r. So if you rewrite it so that it's in this form, and you can identify a and r more directly that way, that's good. Feel free to do so. However, if you want to expand it out like I did at first and go from there, that works as well. I'm not saying one's better than the other, just saying you have 2 possibilities at least here. And of course our conclusions would be the same at that stage. All right, so let's look at this series. n equals 0 to infinity, the number 3/2 to the nth. I'd like to see if we can do this one the second way. So what number is a? What number is invisible that's written in front of that parenthesis? You're right, it's the number 1. And so since it's writable in that form, then that means that it's geometric. Because it's writable in that form, we can say it's geometric. We can say that we now know that a is 1 and that r is 3/2. Now, since the absolute value of this r falls into one of those categories, is the absolute value of this r less than 1, or is it greater than or equal to 1? Well, it is greater than or equal to 1. That implies that the series that we started with, the series that was in question for this problem, diverges. And then that's the end of that problem. If you claim divergence like that, you're done. You don't have to do anything else on that problem. Okay, so looking on the next page, Theorem 9.7, these are properties of infinite series, basically properties of sigma. The sigma of a constant times an a sub n formula. Oh, I should probably write this down. And by the way, these look a whole lot like these similar properties with limits. And you saw all of these actually earlier than this. We're just saying that if we're thinking of this sigma as a series, these properties that you already know are true will hold. So if you have that scalar multiple of your formula, that scalar multiple can come out in front of the sigma, leaving just the a sub n inside. And as you can see in the Theorem 9.7, they've defined sigma of a sub n to be a. So by substitution, that's the c that we pulled out in front times a. The sigma of a sub n plus b sub n is sigma of a sub n plus sigma of b sub n. And up above, sigma of a sub n is defined to be a, and sigma of b sub n is defined to be b. And then a very similar thing happens with the difference of two formulas. You can split that into two separate sigmas, just like you can with limits, and just like you can with integrals. All these properties are interrelated. So they should not come as a surprise. These should look like, oh yeah, that totally makes sense to me. I've done that before. All right, so those are some properties of infinite series. If we need to use them, we will incorporate them. So here's a really important thing. If you want something to converge towards something, don't the values that you're adding, like after that you've added the 99th one, isn't the 100th one going to have to be really small? And that's going to make it not that different from the sum of the first 99. When you add a little tiny number, the sum of the first 100 will not be that different from the sum of the first 99. And that's true for any pair later on. So this next theorem, 9.8, I think should make sense, is that if you're going to have a convergent series, if sigma of a sub n converges, then the only way that that can happen is if those terms are getting smaller and smaller as you go. So if it converges, the limit of the a sub n, remember the a sub n is building the sequence to a series and add the terms of the sequence. So that's the a sub n, is the thing that builds the terms of the series. And if that limit is going toward, will have to go towards 0 if it converges. Each subsequent term you're adding has to be getting tiny, 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 tinier, tinier, and tinier, and tiniest. I mean, you've got to go towards 0. Otherwise, it won't converge. Because if you keep adding like bigger numbers and adding even bigger numbers, it's going to go off to infinity. So hopefully that makes sense to you. Now, I think we talked about this before, but I'm going to state it again because I think it's worth knowing. If you have a statement like the one above, a statement like if something, I'm going to call that something A, then you'll have something as an effect of that. And I'm going to call that result B. If A, then B. The converse of that statement is if you switch the hypothesis and conclusion. The converse of our original statement is if B, then A. Is the converse of every true statement necessarily true? It's really good when I ask that kind of question to make an example for yourself. So let's say A is plays for the Dallas Cowboys, and B, let's make that, is a male. So if you play for the Dallas Cowboys, then you are male. I believe that's a true statement, at least right now, until they hire some woman to do something, maybe as a kicker or something, because they tend to be able to do that really well. I think there was a movie out recently about that. Anyway, is the converse of that statement necessarily true? If you're a male, then you play for the Dallas Cowboys. I don't think so. I don't think my 88-year-old father plays for the Dallas Cowboys. So, no, the converse is not necessarily true. If you have a true statement, its converse is not necessarily true. Now, it could be true. I mean, you could pick a male at random, like, I don't know, I'm going to show my age here, Tony Dorsett, back in that day. If you had picked him back in that era and said he's a male, therefore he plays for the Dallas Cowboys, for him it would be true. Not true for a whole lot of other people, but so we say not necessarily true. Now, the contrapositive statement, the contrapositive of a statement is contrapositive is this. If, then you take the conclusion from your statement and negate it. So if not B, then, and then you negate your original hypothesis, not A. Is that true? If I'm not male, so in other words, if I'm a female, then I'm definitely not, wait, let me say that again. I may have misspoken. If I'm not male, meaning I am female, I think I did say that correctly. If I am female, in other words, then I'm not a Dallas Cowboy player. Is that true? Yes, the contrapositive statement for a true statement, I'm starting to write the wrong thing. The contrapositive of a true statement is always true. Okay, and that leads us to the next thing I want to say is the statement, if sigma a sub n converges, then the limit as n approaches infinity of a sub n has to be equal to 0. That's our statement. I don't know if the converse is true or not. So in other words, if I find that the limit of a sub n as n goes to infinity is equal to 0, that doesn't tell me a thing about the convergence of that series. We don't know. It might actually converge or actually might not. And we're going to see some of those where the limit of a sub n is 0 and it actually does diverge. So kind of keep that in the back of your mind looking for that example. And by the way, contrapositive is all one word. It looks like I wrote contra and then space positive, but contrapositive is all one word. Just penmanship skills are not so great sometimes. So let's take that true statement about convergent series and write its contrapositive, if not b. So we're going to take the conclusion that the limit as n approaches infinity of a sub n equals 0, and we're going to negate it. So if it's negated, that would mean that it's not equal to 0. Then, now we're going to negate the hypothesis of that statement. What is the negation of the series converges? We can say does not converge, and that would be true. Or you could, in one word, say that means it diverges. So right back here, if you want to say does not converge, that's true. Or you can say it simply diverges. This is always true. And in fact, this is what we call the nth term, that's an H, nth term test for divergence. This will only tell you if something diverges. It will not, finding the limit as n approaches infinity equaling 0 is not conclusive. I can't talk and write at the same time because I forget what I'm writing. Sorry about that. If we find the limit of a sub n equals 0 as n goes to infinity, we can draw no conclusions. It's inconclusive. But if the limit of the nth term of that nth partial sum, the general term of the series is something equal to that's not 0, like if that limit is 7, then we can automatically say it diverges and we're done. Actually, you kind of want to see some divergent ones that you can test that way because they're really fast. All you have to do is show that that limit is something that's not 0, and you'll have it. So let's do one, and of course now you kind of know that's what we're looking for. So anyway, and in fact, this is in a list of things to think about when you're testing for the convergence or divergence of a series. This is something you should probably think of automatically first. And if it's going to lead you to divergence, then you write it down. If it leads you to, I don't know, because you get 0, it's not worth writing down. And a lot of times you can just do this in your head. So the nth term of that's a series, oops, I forgot to write the problem. The series is n equals 0
just a sec.
to I said something about series,
I found an answer.
and they thought I said Siri. Oh dear. Sorry about that. Great technology, huh? I'm sorry. Kind of got confused. Oh, not confused, just lost my place. This is the series whose convergence or divergence we're going to test. So the term of the series, the nth term is 2 to the n, and so the limit of 2 to the nth as n goes to infinity is infinite, which is obviously not 0. And so you can say by the nth term test, and you can call it that for short. Up above is what the full name is, but we'll just let you get by with saying by the nth term test, sigma n equals 0 to infinity of 2 to the nth diverges. And this brings up another important point that I'd like to make, is that sometimes there are multiple correct ways to test for the convergence or divergence of a series. In fact, on this one, if I weren't trying to focus on the nth term test, we may have said, oh, that's geometric. There's an understood 1, so a is 1, and r to the nth, r is 2. The absolute value of our r is 2. So that's definitely greater than 1. So the absolute value of r is greater than 1, which would say greater than or equal to 1, which would say, of course, that this one diverges by the geometric series test. So that would be good. Actually, I'm running out of room. I don't have a whole lot left, so the next segment will be really short. Just have 2 examples left. But I'm going to stop the recording now and go to my next one.